Hi students, in this second video for online lecture 14, we are now going to talk about balancing chemical equations. So why do we write chemical equations? Well, it's the process in which one or more substances is changed into one or more new substances is called a chemical reaction. So what we need to do is be able to describe this in the shortest and fastest way we know possible. So a chemical equation uses our chemical symbols, either that from the periodic table or the ones that we have created for our various compounds that we have built, to show what is happening during a reaction. Typically, on the left side, you will have your reactants. These are the species that you are trying to change in order to form our products. The products are your desired species that you would like to make. So let us go ahead and find three ways of representing the reaction of hydrogen gas with oxygen gas in order to form water. The first way is writing it all out. Two hydrogen molecules plus one oxygen molecule gives us two water molecules. This is great, but we live in a Twitter world, and this is getting really close to our number of characters. So we want to be able to write it much quicker than this. This is what we should do and use our chemical formula. So now you can see that I have two H2s plus O2 yields two H2Os. The other way of doing that is using our molecule diagrams that you see at the very bottom. This takes a little bit of work because you have to know which elements you're using, which compounds you're using, and which one and color signify our different atoms. You will work with that as you go on into further chemistries. So how do we read chemical equations? Well, as you can see, I have 2Mg plus O2 yields 2MgO. But what does that really mean to us? Well, we can say that we have two atoms of our magnesium plus one molecule of O2 makes two formula units of MgO. So let's really talk about some of the words that are in there. Why is it two atoms of Mg? Well, it is an element. So in the case of using elements, we need to talk about atoms. So then why do we use the word molecule for O2? It is because our elemental oxygen is in a diatomic molecule form. And then finally, when we use formula unit, that is because we are forming an ionic compound, and that is the term for our smallest form of an ionic compound. But what we can also do is scale this way up. As we saw in the last video, when we could convert from atomic mass units to moles, we are going to do the same thing. So we are now going to go with 2 moles of our magnesium plus 1 mole of our oxygen gas can now make 2 moles of MgO. So you can either use it with atoms or moles, and you are going to have a seamless transition. Then you can also go and use grams, but the grams must be using the molar masses from our periodic table. So we can say that we could have 48.6 grams of magnesium. Notice that that is the mass of 2 moles of magnesium, each mole being 24.3 grams. Then we could have our 1 mole of O2, so it is 16 times 2 to give us the 32. And then finally, if we make our 2 moles of MgO, you can see that we get a mass of 80.6, meaning that each one of our moles would have a mass of 40.3 grams. The biggest concern in all of this is that it is not a 2-to-1 ratio by mass. It is a 2-to-1 ratio when it comes to atoms. It is a 2-to-1 ratio when it comes to moles. But notice that it is not a 2-to-1 ratio for our masses. You must get the correct molar masses from the periodic table, so that way you can do a gram to gram calculation and conversion using our molar coefficients. Do not use the molar coefficients as gram coefficients. You will not get correct answers. So now let's go to a skill that you must come very proficient at over the entirety of this course, and that is balancing the chemical equation. We are going to use these repeatedly through 119 and even more so in Chem 120. The first thing that you want to do is write the correct formulas for the reactants on the left side, our reactants, and the correct formulas for our products on the right side of the equation. This means that you need to take your nomenclature skills that you learned back in previous chapters and apply them here. So if I say that I am going to have ethane reacting with oxygen to form carbon dioxide and water, we need to know what those species are. When it comes to ethane, that is going to be an organic compound, and you'll learn those naming rules later on in organic chemistry. If we start to give you things that you have not seen before, we will historically provide you with the correct formula. However, you know what oxygen is, you know what carbon dioxide is, and you know what water is. So you are expected to be able to use them. So now what you would end up getting is C2H6, which is our ethane, plus O2 yields our CO2 and H2O. Then what you need to do is change the numbers in front of the formulas. We call those coefficients to make the number of atoms of each element the same on both sides of the equation. Do not change your individual compounds once you have them correct. What we mean by this is that we do not want you to go in and change the subscripts of your correct formula because you'll make them incorrect. An example of this is we would need to put 2 C2H6, not C4H12. C4H12 is a completely different compound and one that would lead to an incorrect answer. So once you get through rule 1, you are not allowed to change the subscripts or the identities of any of the species that you write. Afterwards, when you get to rule 2, you are more than welcome to change the leading coefficient to make sure that you have the right number of those atoms. So finally, we get to number 3. We start by balancing those elements that appear only in one reactant and one product. So now you can see that we have our skeletal chemical equation, but there's a huge problem. We can notice that we will start with carbon or hydrogen, but not oxygen. Notice that our oxygen is going to be in 2 different products, and it is going to make our life much more difficult if we try to start with that species. So notice that we have 2 carbons on the left. Well, how do I get 2 carbons on the right? What we can do is go and multiply our carbon dioxide by 2. Remember, that is done by adding a coefficient. You now see that here in our maroon. But now what I can then do is go and balance my hydrogens. So if I have 6 hydrogens on the left, you will notice that I only have 2 hydrogens on the right. So what can I do? Well, we're going to multiply the water on the right by 3. So now you can see that I have our carbon and hydrogens balanced overall in this reaction. So the nice part about it is that we have already taken care of 2 of our 3 elements. We only need to deal with the oxygen next. That comes in with rule 4, and finally balance those elements that appear in 2 or more reactants and products. So now we have our intermediate balanced chemical equation, but we need to deal with our oxygens. So how many total oxygens do I have on the right side? Well, I have 2 on the left. Notice that I have 4 with one compound and 3 in another. So that means I have 7 total oxygens on the right side. So now what I'm going to do is multiply my O2 on the left by 7/2. That way the 2 in our fraction and the 2 in our subscript will cancel out, and you're going to be left with 3.5 moles of that species. So now you will see that I get C2H6 plus 7/2 O2 yields 2 carbon dioxides and 3 waters. But we are not allowed to have fractions in our balanced chemical equation. What we need to do is remove the fraction by multiplying all of our coefficients by 2. So if we do that, you will now see that I get 2 ethanes plus 7 oxygens will now yield 4 carbon dioxides and 6 waters. We must have it in the lowest integer ratio. So finally, what can we do to finish? We're going to check to make sure that you have the same number of each atom on both sides of the equation. So here is our hopeful attempt of our balanced chemical equation. And now you're going to see that I have 4 carbons on the left. I have 4 carbons on the right. I have 12 hydrogens on the left. I have 12 hydrogens on the right. And finally, with my oxygens, I have 14 on the left and 14 on the right. So this means that I have now balanced atom for atom, and this is a successful balanced chemical equation. Let's go ahead and try some examples to get you proficient in balancing chemical equations. Let's start with our top reaction. We have C7 on the left. That means that I would need to put a 7 here for my carbon dioxide. Notice that I have 16 hydrogens, and on the right I only have 2. So what I can do is go in and put an 8, and that will now give me a total of 16. So now I need to figure out how many total oxygens I have. Well, 7 times 2 is 14, and then I get 8 more from our water, so that is a total of 22. So now what coefficient do I have to put in front of my oxygen on the left? Well, seeing that I get 2 for every 1 and I need 22, this means that I'm going to put the coefficient of 11 in front of the oxygen, and now I have a balanced chemical equation. Let's go ahead and look at B, because B is going to have one of the most important rules of balancing chemical equations. We typically call this the polyatomic rule. Notice that I have calcium hydroxide reacting with phosphoric acid, giving me calcium phosphate and water. It is important to notice that my phosphate here in my phosphoric acid stays together and is the same species that we see in the product. So if you have a reaction in which a polyatomic does not break up, you can treat it as a package deal in which you can take it all together. So what I want to do in this case is go and put in a 2 for my phosphate. That way I have my phosphate polyatomic is correct. Notice that I will need 3 calcium, so I can put 3 here. But now we get to a question on how I get water. Well, water in a lot of ways is a protonated polyatomic. You just don't know it and haven't seen it before, but is protonated hydroxide. So now you will see that I have a total of 6 hydroxides here. I have a total of 6 H pluses here. So this means that I'm going to be able to form 6 waters, and you will see that I have a correct answer for B. When it comes to polyatomics, if they stay together, leave them together. So let's go down to part C now. You will notice that I have methane mixing with bromine gas, giving me CBr4, and finally HBr. So what can I do with this? Well, the first thing that we are going to want to do is look and see how many total bromines I am going to need. So as you can see here, I have 1 bromine here and bromines there. So that means that's probably not the best species to start with. So let's start with our hydrogen. Hydrogen, I have 4. So that means I need to have 4 on our right side. Well, now this has changed the number of our bromines. You will see that I have a total number of 8 now. So what that means is that I am going to have to go in and add 4 in front of my Br2. This is a successfully balanced chemical equation. So now let's go down to example D. Which species should I start with first? So I have my iodine, I have xenon difluoride, then I also have iodine trifluoride, and just xenon in its elemental form. So the first place that I would go and look is notice that I have 2 iodines here, but I only have 1 here on the right side. So that means that I will go and put a 2 in front of that. Now that means that I have a total of 6 fluorines. So that means that I have to put a 3 in front of my xenon difluoride. Well, now that means I have 3 xenons. So that means that I have to put a 3 on the other side. So as you can see in my balancing of chemical equations, I will typically alternate side from one to the other. What you do to one side may affect the other. So finally, let's go to example E and you will see that I have what looks like a fairly complex reaction, but it's really nice because I have some polyatomics. You will see them here in ammonia hydroxide. So here is my hydroxide and here is my ammonia. So what I need to do is go and start to look on how to balance this. Notice that I have 3 bromines with my iron. I only have 1 here on the right side. So what I can do is put a 3 over here, and that now gives me 3 ammonia. Well, if I go ahead and put a 3 in front of the ammonia hydroxide, notice that it will automatically balance my hydroxides that you see here on the right side, and I get a successful balanced chemical equation. Using these ideas and procedures are very important, and you want to be able to practice these as much as you can. Our final example for this video, we are now going to have an equation that you see, and then what I need to do is add up all of the coefficients and get their aggregate sum. So the first thing that I'm going to need to do is actually balance the equation. So where should I start? Well, you will see that with my carbons, I have 2 carbons. I have 2 carbons on the right side. I don't have to do anything with that. But let's look at our nitrogen. Notice that with species A, I have 2 nitrogens, while in species D, I only have 1. So what should we put in for our coefficient of D? Well, as you can guess it, I'm going to put in the number 2. So now what we have to look at is our number of hydrogens. So as you can see here, I have 6 hydrogens from ammonia, but don't forget the 2 that is in our acid. So that is a total of 8 hydrogens. So what coefficient do I need to put in front of my water in place of B? Well, if I need 8 and I get 2 for each one, you can guess that I would need the coefficient of 4. So if we were to write this chemical equation out correctly, you would get CN2 plus 4 waters going to H2C2O4 plus 2 NH3s. This would be a correct written answer. But now what we need to do is actually sum the coefficients. This is a problem type that will occasionally trip up people because many students will forget that there is an understood 1 in front of my CN2 and my H2C2O4. We just don't write them in. We don't ever put a 1 when that is the coefficient, but it's still there. So now we need to look at it and say that 1 plus 4 is 5 from this side, and then 1 plus 2 is 3. If we were to sum those together, you will get the correct answer for this problem, and that is problem B. In this video, you saw how important it is to balance chemical equations. As we go into future videos for Chapter 8, Chapter 9, and even into further chapters in different courses, this is a skill that you need to master. Please practice as much as you can to make sure you know how to do this. Have a great day.